To design our counter, we first needed to understand how the counter behaves from 20 to 0. We divided the counter into two sections. A 2 to 0 counter for the most significant bit, MSB, and a 9 to 0 counter for the least significant bit, LSB. These truth tables were essential in identifying flip-flop output condition of the JK.
Using the truth table for the 2 to 0 counter, we derived the Boolean expressions using couple maps. For example, for J1, we use the expression J1 equal to Q1 times Q2 complement plus Q1 complement times Q2. And it's simplified from using don't care conditions, is Q2 plus Q1. Similarly, for J2, we simplify it to just Q1 complement. Next, we focus on the 9 to 0 counter. This part is more complex as it involves for JK flip-flop. For instance, J2 was simplified to Q1 complements in bracket Q2 plus Q4 plus Q3. And J3 become Q1 complements in bracket Q4 plus Q2 complement times Q3 close bracket. And J4 was Q1 complement times Q2 complement and Q3 complement. These simplified Boolean expressions help us implement the circuit efficiently.
Now I'll explain the most critical part of our project, which is the final counter Boolean expression. In the circuit, we divided the counter into two parts. The first part is the most significant bit, which count from 2 to 0 and use flip-flop group B. The second part is the low significant bit, which count from 9 to 0 and use flip-flop group A. These two parts work together to perform a countdown from 20 all the way to 0. The final counter logic combines both MSB and LSB expression. This Boolean equation ensures that the LSB count down from 9 to 0, the MSB decreases after every full LSB cycle, and the whole counter reset after reaching 0, 0. This design allows our counter to accurately count from 20 to 0 and restart automatically. Once the logic was finalized, we built the circuit using multi-sim software. We connected all JK flip-flops and logic gate as per our derived expressions. The simulation demonstrated that the counter correctly counts down from 20 to 0 and then loops back.
To verify our design, we observed the timing diagram of both 2 to 0 and 9 to 0 counters. The diagram shows the correct transition of output states on every clock pass. It also helps us detect small glitches that may happen due to asynchronous triggering.
In conclusion, this project allows us to successfully design and simulate a 20 to 0 decimal counter. We applied concepts like truth table, Carnot maps, Boolean simplification, and digital simulation for it. Even though we face challenges like glitches, we propose solutions such as adding debounce and synchronization circuits in the clock. This project has really enhanced our understanding of sequential logic and JK flip-flop operations. That's all from us. Thank you very much.